Today we're going to continue talking about boundary layers. If you recall, last class we were talking about several different thicknesses of the boundary layer. We talked about the disturbance thickness, or delta 99. We talked about the displacement thickness, or delta star, and we talked about the momentum thickness, theta. And each of those quantities were different ways of us to express the boundary layer thickness. And as it grows, as we move downstream, or as the Reynolds number increases. We're going to continue talking about the boundary layer today, and the first thing that we're going to talk about is actually the boundary layer equations. And the boundary layer equations, these were derived by Prandtl back in 1904, and they start from the basic Navier-Stokes equations. And we've talked a little bit about the Navier-Stokes equations, and the set of equations that we start out with that we have, so something that looks like a U component of the momentum equation. So the Navier-Stokes equations are fundamentally F equals ma, and it looks, if we look at it in 2D, we get something that looks like this. And we talked about this a little bit earlier in class. And this is not a major part of ME 3710, but is a major part of ME 576700. But it's important to kind of have an idea what these partial differential equations look like. So we have our unsteady term here on the left. We have our advection or convection terms, and then we have minus 1 over rho dp dx, so that's pressure, plus nu times d squared u dx squared d squared u dy squared. So this is the x component of our momentum equation. And as I said, we have a time-dependent term. We have that are associated with our inertia here on the left-hand side. This whole thing is like dv dt, or it's our big du dt. We could write that as big du dt. Going back to thinking about Eulerian and Lagrangian descriptions. So we have our inertia here on the left-hand side, inertial terms. Then we have a pressure term and a viscous term. So those are our balances that we're focused on. For the moment, again, we're neglecting the buoyancy forces. And for a lot of our airflows, this is airflow and neutral stability, it's not a problem. So meaning just no buoyancy acting. So that's our x component of the momentum equation. And then we're going to have dv dt, which is going to be our y component of the momentum equation. So dv dt plus v du dx plus v dv dy minus 1 over rho dp dy now. And these are d's. Nu d squared v dx squared plus d squared v dy squared. And that's going to be our big dv dt. So hopefully that makes sense. And actually, in the most formal sense, we'll keep these as partials because not yet. This is our general form that we're looking at for 2D. So this is going to be 2D Navier-Stokes equations. And then usually to go with that in 2D, we'll have our conservation of mass equation in differential form, du dx plus dv dy equals 0. And what Prandtl did in his development of these boundary layer equations is he made some important simplifications that we talked about in last class. Remember, we said that the vertical velocity v is much smaller than the horizontal velocity u, and also we said that the gradients in the x direction are much smaller than the gradients in the y direction. And if you go through and look at the equations term by term, and if we assume that we have a steady boundary layer, then, well, steady allows us to cancel these terms out. And the idea of the small vertical velocity compared to the horizontal velocity and the gradients allow us to make a couple more simplifications. And so here in the x momentum equation, these go away. And actually, what we see in the y momentum equation is actually everything goes away except for the pressure gradient. And so ultimately, our boundary layer equations, and we'll focus on the x momentum equation. As I said, you only have a pressure gradient in the y that's left. That is dp dy equals 0. That's an important result, actually. So we'll write that down too. So u du dx plus v du dy equal minus 1 over rho dp dx plus nu d squared u dy squared. That's our key momentum, x momentum equation. And then our y momentum is going to be simply dp dy is equal to 0. And then we're going to have our conservation of mass equation, du dx plus dv dy is equal to 0. Okay, and actually the dp dy part equal to 0 is really important, because what it ultimately is going to tell us is that if we have a flat plate boundary layer that are basically it's the kind of concept that the streamlines are parallel and that we don't have a gradient in the direction normal to the wall. That is, we have our wall here, and we have some almost parallel streamlines. They're not, because the streamlines have to deflect a little bit because we have a non-zero v velocity. It's just very small here. And then one of the things that Prandtl focused on after that was the zero pressure gradient boundary layer. So this is a general boundary layer that has a pressure gradient. If there's no pressure gradient, then this term goes to 0, and then we simply have a balance between advection and diffusion. And that's what we talked about before, that we have this balance between advection and diffusion. And that's a key part of what a boundary layer is, this balance between advection and diffusion, unless we have a pressure gradient. And in fact, today, that's going to be one of the key things that we're going to talk about. So Blasius solved, so Blasius, as I said yesterday, was the student of Prandtl, and he solved the boundary layer equations. That is the equation for the zero pressure gradient. So he solved the du dx plus v plus u dv. Oops. Yeah, we'll just put it on the next page. His solution here was u to the equation u du dx plus v du dy equal nu d squared u dy squared. That is our momentum equation without the without the pressure term. So this is a zero pressure gradient boundary layer, and that plus du dx plus dv dy, or conservation of mass. Okay? And his solution that he came up with, he actually took this partial differential equation. This is a second order nonlinear partial differential equation. It's nonlinear because we have a product between a velocity and its derivatives. So these are the nonlinear terms of the Navier-Stokes equations. And then this is second order because of this term here. So it's second order nonlinear differential equation. And he reduced it to a third order ordinary differential equation. It's a nonlinear ordinary differential equation, but he reduced it to a first order. And actually, to solve it, he used what was called the shooting method. And the shooting method you should have learned in numerical methods, and the shooting method is a technique that we use to solve ordinary differential equations. So he did this conversion from the PDE to the ODE, and in doing so, and if you take ME 5700, 6700, you can do this yourself. In doing so, he came up with a solution. And because it's numerical, actually a lot of times we just tabulate the results, and that's what this slide is showing you here. On the right-hand side over here, we have a plot of the non-dimensional vertical coordinates. So if we normally would have our boundary layer wall here, and so this is the x direction, and this is the y direction, and our boundary layer is growing like this, and we have delta, and then we have a profile. So this is a profile, and out here this is u infinity, our inviscid region. These plots are now only in the viscous region, and eta that we have is equal to y over delta. But in in his solution that he came up with, delta is actually equal to, and you can see here we multiplies this by u times, so that you have y times u divided by nu x to the 1/2, and this is just ends up being in the denominator. So our delta that is described here is, as I said, is like nu times x over u to the 1/2. So that's this term that ends up that we're talking about here in the this is, I just flipped it over so that it's consistent. So when we plot these solutions, we can think of eta as being y over delta, and that's over here. So y over delta, a non-dimensional wall normal coordinate. And then on the x-axis, we have u over, the textbook uses big U, but this is, I call it u infinity. So this is the solution that we have. And you can see the shape of the plot here that we have. So this is the profile. And a couple important quantities that show up. We see that our so-called delta 99 that we define. So delta 99 would be, this over here. So again, eta equal y over delta. We get a velocity that's 0.99. So u over u infinity is equal to 0.99. That's our delta. That's our delta 99. And eta is equal to 5 at that location. Okay, so that means that eta, which is equal to y over delta, is equal to 5 when we have u over u infinity equal to 0.99. Okay, so that's the non-dimensional version of the solution here on the left-hand side. On the right-hand side, there's the dimensional version of the solution. So you can see the different locations. Here we have x1, and then x2, x3, x4, and x5. And as we move downstream in real dimensional space, you can see how the boundary layer is growing. But what's really cool is when we non-dimensionalize it with y over delta, or this eta term here, as a function of u over u infinity, we just have one plot. And so we can actually plug in the values. So if you have a specific value of x that you're looking at, then you can plug in that x value. And if you have a specific u infinity that you have here, you put that in. So you say, okay, my free stream velocity is 5 meters per second, and I'm 3 meters down the length of my plate. Then I now know what delta is, and so I can compute the profile y over delta for a specific location downstream. Okay, so that's the laminar-Blasius solution, and it's discussed also in the textbook in Chapter 9. But the most important thing is this gives us this laminar exact solution. And we also have some other solutions, for example, approximations like a second-order polynomial. Once we have a solution, so that is we have a solution to the velocity, so we can say that u is equal to something, then that's our velocity. So u is some function of y and x in our boundary layer. Then we're able now to compute the length scales that we talked about last class. So if we take the Blasius solution and we plug it in to our various equations for delta star and theta, then first of all, this is the exact solution to the boundary layer perturbation thickness, delta, because it was an actual analytical solution solved with the boundary condition that says that as y goes to delta, u goes to infinity, we actually get a nice solution for delta here. But we can take this velocity profile that we have from Blasius, and we can plug it in and actually integrate it and actually get a solution for delta star and theta star. So anytime we have, again, say if we think about delta star, this is the integral from 0 to, say, infinity, but to usually we just integrate it to some finite length like delta, and then we have times 1 minus u over u infinity dy. So once we have that profile, u of y here, then we can integrate it to get our displacement thickness, or we can also get it to get the momentum thickness. And so that's for the laminar cases. And then for a turbulent boundary layer, just like for pipe flow, we can use a power law description. And say, for example, if we have a power law of 1/7, then we can plug this into our equations for delta star and theta and get our different solutions. And this is an example of how delta behaves. We also define something that's called a shape factor, which is the ratio of the displacement thickness to the momentum thickness. And its behavior, this ratio, is a bit interesting. So you can see that for laminar flows in a zero pressure gradient, we have a value that's about 2.6. And then for turbulent flows in a zero pressure gradient, we have a shape factor that's about 1.3. So the ratio of the loss of mass flux to loss of momentum flux in the boundary layer is very much dependent on the shape of the profile, which is exactly what we're saying. We're integrating that profile, and so that should make sense. What do some of these actual quantities, we have these equations here, what do they mean, and how do they behave? Because there's some really interesting things that we see here. So for example, here we see that the boundary layer thickness varies like 1 over the square root of the Reynolds number. Okay, so this is delta over x. So at a particular, as we move downstream, x is changing, and so is the Reynolds number. So we want to see, how does that boundary layer thickness change? It's growing, and it's growing like 1 over the Reynolds number. Okay, so RE x to the minus 1/2. And then similarly, we see that that we have the displacement thickness and the momentum thickness. They both also grow for a laminar boundary layer like 1 over the square root of the Reynolds number. Whereas for the turbulent boundary layer, it grows like 1 over the Reynolds number to the 1/5 power. So conceptually, what does that mean? We're going to, and I'm going to jump to that curve here. So these are these profiles. So here on the left-hand side, I have a plot of laminar, and the blue line is the laminar boundary layer, and I'm using a second-order polynomial. It's just easier to plot, and then the turbulent profile, which is the 1/7 profile. So you can see a big difference here. You can see that there's much more momentum closer to the wall in the turbulent case than there is in the laminar case. What about the growth of the boundary layer? So this is going to be delta as a function of distance x downstream in the boundary layer. So again, if we have our flat plate that looks like this is our x direction, this is our y direction, the boundary layer is growing, right? So how do I actually calculate delta? Well, I can do it using these equations that I've talked about here and what they look like and what's really important. So here I have calculated a single, we have various Reynolds numbers, but it's for a single velocity. So imagine you're in a wind tunnel and you set the wind tunnel velocity to free stream velocity, u infinity, to 5 meters per second. And then let's see how the boundary layer grows. And you can see for the first 1.5 meters or so, maybe a little bit more than that, we have a laminar boundary layer, and then somewhere around here, this is about 500,000. This is where we have our transition to the turbulent boundary layer. We go from this very slowly growing laminar boundary layer to our turbulent boundary layer, which is growing more rapidly and becomes much thicker for the same velocity. So what I've done here is I've simply plotted the two equations. So I've used, for the laminar case, I'm using this equation, and for the turbulent case, I'm using this equation. Similarly, we can look at the variation in the wall shear stress. Now remember, what is the wall shear stress? Well, tau at the wall is equal to